Good evening, everyone. We're the Taper Factor group from the Material Science and Characterization Lab under Dr. Steristina. And today we're going to be talking about determining taper factor as a function of grain size strengthening mechanism. The presenters are Nicholas, Anna, Timothy, Shoyo, Saket, Aaron, and me.
Okay, so the Tabor factor. The Tabor factor, or the constraint factor, is a measure of the plastic properties of solids that was first defined by D. Tabor or David Tabor in 1951 as hardness divided by stress at 8% strain. So the first measurements of the constraint factor were performed on mild steel, annealed copper, and lead telluride. So he eventually concluded that C, or the Tabor factor, is about 3 for all polycrystalline materials. The formula for the Tabor factor, as you can see, is hardness over stress at 8% strain, but it's important to know that it is not yield strength, which is stress at 0.2% strain. And some important assumptions for Tabor factor calculations are that A, the solid is isotropic, B, flow stress is constant, or UTS is equal to yield stress, which happens at a considerable amount of strain, such as 8%, and C, elastic deformation is unimportant. So essentially, the Tabor factor is used in industry to predict yield strength or the maximum amount of stress a material can withstand. Next slide. Okay, so there are different mechanisms of strengthening metals. First is grain size strengthening, which is making all the grains in the material smaller so that the total length of all grain boundaries becomes longer and effectively acts as obstacles to dislocations. So as you can see on the picture on the right, the red lines indicate where the grain boundaries are. So grain size strengthening is what we are currently doing by annealing our copper samples at different temperatures such as 700 degrees Celsius, 800, and 900 to see how much the grain size may affect Tabor factor. There's also alloying, which includes both substitution and interstitial, where we basically combine two metals together to form a stronger alloy. There's second phase strengthening, where we introduce second phase particles that hinder the movement of dislocations, which increases the material's resistance to deformation. And then finally, there's strain hardening, which is a process that hardens the material by plastic deformation. It is also known as work hardening or cold working. Next slide. All right, so the Hall-Pitch equation. So this equation essentially describes the relationship between grain size and the yield strength in polycrystalline alloys. And also, grains are individual crystals that make up polycrystalline metals. The boundaries or the areas of misalignment are called grain boundaries, as said earlier. There is a reciprocal relationship between grain size and yield stress, according to the Hall-Pitch equation. So in simpler terms, it's the smaller the grains, the stronger the material. And literature reports of about 60 years of data are on the yield strength of metals at different grain sizes. The example data for copper is seen on the right. And as you can see, calculating strength from hardness, assuming that the constraint is 3, leads to a lot of inconsistencies. So in our project, we are adding to the experimental database of 60 years and comparing our results to the already existing data to see whether we are on the right track or not.
For short-term goals of the study, we plan to conduct rigorous hardness tests at the 3 annealing temperatures that we have annealed copper samples at, which is 700 degrees C, 800 degrees C, and 900 degrees C. And we need to calculate the Tabor factor for each grain size. We also plan to compare our data to the literature data, and depending on the results, we decide on what to do next. In terms of long-term goals of the study, we plan to anneal more samples, conduct more tensile tests, and Drucker hardness tests to see if grain size affects the Tabor factor of annealed copper.
So now on to how we prepared our samples. So to start off, we purchased sheets of copper 110 from McMaster Car, which was at an ASTM B152 spec, which is a specification for copper sheets relating to things like resistivity. In the lab, we then created CAD drawings, which we can see in the diagram at the top, which were to be used in the machine shop over at Santa Clara University. Using these diagrams, we machined 5 copper specimens to be used for tensile testing as spec to the ASTM E8 specification, which is one of the most common methods for determining the tensile properties of metallic materials. After our tensile testing concluded, our 5 samples were then annealed in a Gizmet furnace in lab at 3 separate temperatures, 700, 800, and 900 degrees Celsius for around 1 hour. Next slide. Now here's some of the methods that we use to get our data. So to start off with the tensile testing, the testing at SCU gave us data, which after some calculations, we graphed and used to obtain the Young's modulus, yield strength, UTS, and ductility. This helps us to determine whether our tensile testing was successful or not, allows us to relate back the data of previous works. Afterwards, using in-lab equipment with the annealed samples using a Buehler auto polisher, we polished our samples at different grits until they obtained a smooth mirror finish. These samples were then etched using nitric acid to attack the material between the grain boundaries, which allows us to see the grain structure. Then, using optical microscopy, these grain boundaries became visible, as we can see in the image in the middle. Then, using image analyzing apps like ImageJ, we employ the linear intercept method to calculate the average grain size. The linear intercept method is a method that involves 10 randomly placed lines, and these lines are then calculated for their length, which in our case was in micrometers, and the number of visible grain intercepts. When you divide the average line length by the average amount of grain intercepts, you can get the average grain size. However, something to note is that in our calculations, we do not take into account twin grain boundaries, which is when the grains look like a mirror copy of each other. Finally, to verify our results, we use EBSD, or electron backscatter diffraction, which we did over at JH Technologies. EBSD is a technology which is commonly used to study the structure of crystalline metals using Kikuchi lines. Yeah.
This is our data using electron backscattering diffraction. On the left, we have samples annealed at 900, 800, and 700 Celsius, and the data collected at the bottom. Average grain size is determined from the field average of grain areas based on the number of points on the EBSD map. This is done by placing a specimen in a scanning electron microscope, or SEM. The electron beam interacts with the material, producing diffraction patterns that reveal the crystal orientation at each scan point. And then individual points of the scan are grouped into grains according to their orientation. EBSD has advantages over traditional optical grain size measurement techniques, particularly for materials where it's difficult to properly reveal grain boundaries using standard metallographic preparation methods. Although it's really helpful, this method can lead to discrepancies in our data. And then on the next slide, you can see the graphs of the grain distributions on the left, and then on the right side is the grain boundaries, and then the min, max, and average diameters on the right. So, however, in our data, there are 2 more additional factors that can lead to discrepancies in our data. So when performing EBSD, twin grain boundaries are also taken into account, changing the actual grain size measurements. The orientation of our sample when doing the testing can also alter the grain size because grains are smaller on the side than the middle, so it will report the tiniest grains from the perimeter. And then here we also use stitch images, which is when images do not contain enough grains for us to get a proper measurement. We can use multiple images together to get more accurate results.
Now let's take a look at our optical microscopy images. So these are 3 of our samples at 900, 800, and 700 degrees Celsius. And we can see the grain distribution is 360 for the 900 degree sample, around 300 for the 800 degree sample, and around 175 for the 700 degree sample. And again, we can see that there is a big discrepancy between our optical microscopy and our EBSD images. And again, this is due to a multitude of factors, including EBSD taking account taking twins into account, as well as our metallographic polishing and etching procedures not being 100% perfect, as is not possible. So it's not 100% clear just visually where one grain ends and another one begins, which is why EBSD is such a helpful tool for determining grain size through crystallographic orientation. Next slide, please. And now let's also take a look at our stress strain diagrams. And so these were our samples that we did tensile tests on at Santa Clara University. And we can see here that we've calculated a whole bunch of values through looking at this diagram. So at the very bottom left, you can see we calculated our Young's modulus, and this is where you can elastically deform the material. That is, you can deform the material, pull it, without it permanently deforming in shape. And from that Young's modulus, which is calculated to be around 22,000 for this 700-degree sample, we then found the yield strength at 0.2%, and we also found the yield stress at 8%, which is crucial for our later measurements for the Tabor factor, as this is what is the standard practice for calculating the Tabor factor is with yield stress at 8% to get rid of any work hardening that may affect the yield stress. Yeah, and then we also calculated our UTS and our ductility for these samples. And we did this for all 5 of our samples. And that's why we can see trends in our data. We have 2 sets of data. We have manually calculated data on the top, as well as automatically calculated instron data at the bottom from our tensile tests. We chose to do manual tests because we believed it would be more accurate. And we can also see that in addition to calculating all of these values, we can see in our samples that there is significant necking along the fracture point, which means that our samples experienced ductile failure instead of brittle. And however, we did identify a sort of problem, which is that in our furnace, there is a temperature gradient where the top is, we think, significantly colder than the bottom of our sample. And this leads to inconsistent heating as we anneal our samples. And this is significant because if you have inconsistent heating, that means that because of the temperature gradient, the grains at the top will have a drastically different size compared to the grains at the bottom and compared to the grains in the middle. And this is something that we can see in our samples, where the top has a much finer grain structure than the coarse grains at the bottom. And we believe this is due to incomplete recrystallization of our samples. However, this isn't all bad, as because we have this temperature gradient, we are able to perform more Vickers tests and do more grain size analysis, which is good for collecting more data.
So another thing we're doing is compiling our literature search data so we can compare it with other studies and ensure that the data we're getting actually makes sense. Mainly, we're looking at the y-intercept and the slope of the trend line. And most of the data points we have right now are from the literature search, but in the red circle, we have 3 of our own data points for samples annealed at 700, 800, and 900 degrees Celsius. For our compiled dataset, we found that the friction stress is 21.9 megapascals and the slope is 0.101, which is really close to the constants from Wikipedia and the results of other studies that have done similar tables. So we are comparing our compiled data using 2 equations. One is the Hall-Petch equation, which is the relationship between yield strength and grain size. And also we have an equation for the relationship between hardness and grain size. And we're looking at the friction stress, which is the y-intercept of the graph, and refers to the yield strength of a single crystal or the intrinsic resistance to dislocation movement. And we're also looking at the constant K, which is the strengthening coefficient. And even though our furnace didn't work like Nicholas mentioned for our tensile test experiments, since the temperature varies throughout the crucible, a positive is that we can get data points for how hardness correlates to grain size, and we can find these constants and make graph similar to the one on the bottom right.
These are our future steps. We will be performing the Vickers hardness test to obtain hardness values at different grain sizes, including the as-received copper sheet and the top and bottom of the tensile test samples. We will calculate the taper factor for each grain size using the measured yield stress at 8% strain values from the tensile test as per definition, and do the calculations for the ultimate tensile strength. We will refine the estimates for material constants, friction stress, and slope. We will use a better furnace or develop a new way to evenly heat treat the samples, because our research can't properly continue until we find a way to evenly heat the specimens. We will do the improved heat treatment and tensile test for the 400, 500, 600, 700, and 900 degrees Celsius, and we will analyze all data to see if and how the grain size influences taper factor. These are our references. We would like to give our acknowledgements to our parents, ASDRP, Dr. Saracino, Santa Clara University for providing us with specimens and performing tensile tests, JH and JH Technologies for donating their polishing supplies and performing EBSD imaging.